Yeah, so which of these will have optical isomer? How do we answer a question like that? Basically, we just look for a chiral center. Now, what's a chiral center? It's a carbon that's attached to four different groups. So let's look over here. Uh, Double bond means it's just attached to one thing twice, so it doesn't really count. You need four different groups, so this doesn't work. And so this is cancelled out, this is cancelled out. This C is attached to three hydrogens. So you have four, you need four different groups or ये तीन hydrogens से join है. So this isn't going to work. All right, let's look at the next one. This carbon is attached to three hydrogens, so it doesn't work. This carbon is in a double bond, it can't be joined with four different groups because of that. Okay, let's look at this carbon. This might sound interesting because it's attached to a carbon here, it's attached to a hydrogen, it's attached to a chlorine, and it's attached to another carbon. So because of that, this is a chiral carbon. If I were to draw it, this is how I will draw it. So I'll put that carbon in the center. I will have hydrogen on one side, chlorine on one side, CH3 on one side, and the rest of it on the other side, which is what? CH double bond with C, CH3, 2, that whole thing. This is my chiral carbon, which means I will get enantiomers. Enantiomers are isomers that are mirror images of each other. Let's try to make a mirror image of this thing. How would I do that? Sorry. I will put a, sorry. I'll put a dotted line here. This is my mirror image, my mirror in fact. And then I'll put carbon here and just reflect everything. So the dotted line comes here, CH3. The wedge will go there. ऐसे ही होगा. Yeah, Cl, the solid line here, and that whole CH double bond C CH3 2 here. So all of it is reflected. So I know right away that this is optical isomers. These are two chiral carbons, like one chiral carbon forming two optical isomers. And why is it chiral? Because it's joined to four different groups.
Sir, why is there a dotted line with CH3?
So basically, we get a 3D formula. In a 3D formula, you have a solid line here and here, a wedge, and a dotted line. What does it mean? That wedge means that this is outside. It is like if you're looking at the screen, it's coming towards you, it's outward. And that dotted line means inward. That's it's behind the screen that you're looking at. And this is on the page. And that's also on the page, but at the top. So that's a 3D formula.
Okay.
That's why it has a dotted line. Yep. All right. Try to make a 3D formula of this simple compound, CHBrClF. Make a 3D formula of this thing. Always take a carbon like that, put the standard 3D formula on it. There you go. That's a standard 3D formula. Now, one has H, one has Br, one has Cl, one has F. Now, because you're just in A levels, we are keeping things simple here. I know you don't believe me, but we are. So it doesn't matter where you put which group for now. Okay. In A levels, it doesn't matter. Later on, obviously, if you're going into organic synthesis and all, it will matter a lot. In fact, it can become a life and death situation in some pharmaceutical industries. All right. So this thing, this is a chiral carbon, as you can see. Why? Because this is attached to four different groups. There's a chlorine, bromine, fluorine, hydrogen, all four distinct groups. We usually denote it by a star on it just to show that this is chiral. And we can make its enantiomer. Enantiomer, yani ke its mirror image, by putting the carbon here. Now, you have studied O-level maths, and this is reflection. So you take this thing here, the wedge is towards the right on this one, so we draw it towards the left on this one. The dotted line is on the left, so we draw it on the right, and we just put the atoms there. And yeah, if we were able to extract the video from yesterday, you'll see why this is completely different from each other. They are not exactly the same. In fact, they're mirror images. All right. So that is optical isomers. Let's try to do cis trans isomers. So for example, the simplest compound is butene. So I have butene. Okay. So I take this one. Uh, let's draw it. So this is C, four carbons in the chain, then sorry, four in the chain, right? So the second one has a this branch, and we put the hydrogens here, everything here, everything here. Now here's the thing with cis trans isomers, and pay attention to this. Whenever you want to draw a cis trans isomer, just focus on this standard diagram. This is our standard diagram for cis trans isomers, just like that was our standard diagram for 3D structures. So now you're going to put the groups here. So this carbon in the middle, it's attached to a hydrogen here, and it's attached to this whole thing, which is a CH3 here. Why did I not open that up? Because I want to focus on the double bond now. Similarly, this one is attached to a hydrogen here and the methyl group here. So yeah, why can this show cis trans isomerism? Number one, this has a double bond. That is why it can show a cis trans isomerism. Second, it has the same thing attached on either side. Like this has a methyl, this has a methyl. Or if you don't like methyl for some reason, then this has a hydrogen and this has a hydrogen. So there you go. These are the two same groups. And on every carbon, there are two different groups. Like this one has a hydrogen here, but also a methyl here. Similarly, this one has a hydrogen here, but also a methyl here. So how do you know it's a cis trans? Must have a double bond, must have same thing on both sides, but that's not necessary. But it must have different things on each carbon. Each carbon must be joined to two different things and a double bond. And those two requirements, if they're fulfilled, you can get cis trans isomers. All right, so how do we get cis trans isomers here? So the first one is obviously the one that I've drawn. So this is cis trans isomer, but which one, cis or trans? Let's see. The methyl group is on the same side of the double bond. So this is cis, same side. And this one would be, if I keep the CH3 here and the H here, but switch the other two. Notice that I cannot rotate it. Why? Because there is limited rotation of the double bond. And now the methyl group is on the either side of this. And because of that, this one is on the opposite side, the either side. So it is going to be a trans. So that's a trans, which is on the opposite. And this is cis, because it's on the same side. So that is how we get cis trans isomers. All right. You can get the same thing. I'm going to give you a compound. Try to draw a cis trans isomerism of that thing. All right. So how do we do this? We draw the standard diagram for cis trans. Okay. And then on the left carbon, I have a hydrogen, I have a fluorine. On the right carbon, I have a hydrogen, I have a methyl. Now, what is this thing that I'm going to focus on? I have hydrogen on either side, so I'm going to focus on hydrogen. It's your choice. You can focus on fluorine and methyl. That's perfectly fine. So this one, because they're on the same side, this is cis, and this one, they're on the opposite side. Now I'm going to keep this one the same, but switch the other two. Again, it is switching. It's not rotation. Remember this thing. Double bond has limited rotation. You cannot just randomly rotate one side. You will break the bond if you try to do that. Basically, you have to make the molecule again and make sure that you're getting this isomer. All right, so there you go. Now, in this case, hydrogen is on the opposite side of this double bond. Sorry. So this is trans. Okay, so cis and trans. Now I'm going to give you a molecule and tell me why this will not have. So this molecule, why can this not have cis trans isomerism?
Because there isn't a second molecule on the left side.
There is a second. What do you mean second molecule? We need to use the correct terminology. So do you mean there isn't a different atom on the carbon? Yeah. So on this carbon, it's not attached to two different groups. So if it's not attached to two different groups, that means it can't have cis trans isomerism. So that's why. All right. Now, again, this is something that has never been tested on A-level exams before, the one that I'm about to discuss. But I'm expecting it to be from 2023 onwards, because there has been some discussion on this in the new chemistry book that we just got last year. So, for example, this is compound. I have one bromo, two chloro, cyclobutane. Now, this is a interesting kind of cis trans isomerism because it's not going to happen on a double bond. It's going to happen on a single bond. So, what cyclobutane? Cyclobutane is basically four carbons in a cycle. And the first one over here has bromo. So, there's first one with bromo, and second one has chloro. All right. So, how will this show cis trans isomerism? Basically, think of this as one plane, like this carbon joined to this carbon joined to this carbon joined to this carbon joined to this carbon. And they all have hydrogens there. Like this one has hydrogen above, hydrogen below, above, below, above, below, and above, below. Now, this one, if it has bromine above it and chlorine above it, they're both on the same side of the molecule. So we say that this is cis. All right, there's in the same side of the molecule. But the same thing, if instead of having this, they move the chlorine to, let's say, this side. Now they're on the opposite side of the ring that you have, like this ring. So if I were to join them now, this makes a shape like this, and this is a shape like this. So this is cis because they're on the same side. This is cis. And this one is trans because this is on opposite side. Again, this has never been tested in A levels, but I have a strong feeling that it will be from next year. How do you draw this? How do you draw this using three-dimensional formula? So things that are above, we can show them using a wedge. So if both of them are above, that will be a wedge. And the things that are behind, like below the plane, we can show them as dotted. So this shows that this is one is outside and one is inside. This is trans, and the left one, they're both on the same side. They can both be inside. Like you don't have to draw a wedge. You can also draw it like this. Like this is dotted, this is dotted. That's fine. They're both behind it. Or they can both be in the front, and that will be cis. But that is trans because that's on the opposite side. All right. Okay. All right. Now the next thing I want to focus on is identifying the chiral center. So let's say I have this thing. Let's try to name them. What is the left one? What family does it belong to? It has just single bonds. So it is alkane. It's a cycloalkane. And which one? It has six sides. So cyclohexane. But it also has a branch on the first one. Like this one has a branch. And this branch is one carbon. So one methyl cyclohexane. But the other one is not alkane because it has this thing, which is C double bond O. What is C double bond O? We have seen this before. This is ketone. So this one is not cyclohexane, it's cycloketone. Okay, so this one is cyclohexa because six known cyclohexanone. Now this makes this one the first carbon. And so we have a methyl on the second one, 2-methyl cyclohexanone. Okay. Now remember one thing. Every carbon is joined with as many hydrogen as it needs to fulfill 4 bonds. For example, this carbon over here has 1 bond, so it will be joined with 3 hydrogens, sorry. And this carbon over here has 2 bonds, one on below and one above. So it will join with 2 hydrogen, ek idhar, ek idhar. Similarly, this one has just 3 bonds made already. So it will be joined with 1 hydrogen. We usually don't draw them inside. We draw them outside like this one. So it has CH3 here and H here. All right. Can we figure out chiral centers here? Let's see. Now, chiral centers are important to identify, okay? All right. So what is this carbon, this one? How many groups is it attached to? Is it attached to 4 different ones? So it is attached to hydrogen, that's 1. Methyl, that's 2. But this thing here and this thing here. Either side, there's the same thing. So it's not attached to 4 different groups. This one and this one are identical. So we say that this is not chiral. All right. Look at this one. This one is attached to hydrogen here, methyl here. Okay. Hydrogen is 1, methyl is 2. This ketone part is 3, and this simple carbon chain is the fourth one. So this is attached to four different ones. So we'll say that this is a chiral carbon. There isn't any other chiral carbon. Reason, for example, every other one is attached to two hydrogens. All right. So they're not chiral because they're attached to four. They are not attached to four different ones. Every one of them has two hydrogens attached. And this one has oxygen attached by two bonds. So it needs four bonds. उसमें से दो उसने एक के साथ बना लिया. So this is not chiral.
So how is the one chiral, the one that was talking about?
So this one has hydrogen, that's one, methyl, that's two, the ketone part, three, and the simple carbon chain CH2 on this side. So four different groups on either. So because it's attached to four different groups, we say that this is chiral. As long as you have four different groups, the thing will be chiral. Let's try to analyze these two molecules. I usually give them to my O-levels class, so we can still identify them. So what functional groups do we have here? So this one, what functional group is this?
Hydroxy.
Hydroxy, or you can also think of it as alcohol, both of them. What is this one? In fact, let's leave that out. What is this one? NH2 is amine. So this is amine group. This one is amide group, or we also call it peptide if it is in natural compounds. So this is peptide or amide. All right, so amide group. This one is a carbonyl group because C double bond O. This one is an amine group again. So this one is carboxylic acid, and this one is a thiol. We don't study thiols in A levels, maybe in a few years. What is this one?
So carboxylic acid.
Perfect. And this one?
I'm not sure about that one.
If you're not sure, open it up and see what it becomes. What do you think?
So is it ester?
It is ester, yes. We have this molecule here. Do you think this is chiral? Do you think it's chiral?
I don't think it is.
Why not? For anything to be chiral, it should be attached to four different groups.
So would the methyl group and the other CH2, CH3 count as like the same?
No, why would they? This is methyl, this is ethyl. They're two different groups. All right. So this is chiral, this one. All right, let's try this one. Which of these is chiral? Yeah, the one on the left, yes. The second one is not chiral because it's attached to a hydrogen here and a hydrogen here. Or it could be methyl, I'm not sure. They haven't shown what it is doing. So if this one is chiral, can you draw its enantiomer, its mirror image? Try drawing that. It is chiral, by the way. So try drawing its mirror image. What would it be?
Sir, what's the point of drawing the mirror image?
Because a mirror image is a different isomer. It has a completely different properties than this one. Yeah, just like your hands. Whatever you can do with your left hand is not exactly what you'll do with your right hand.
Okay.
Yeah.
So they'll only ask us in the exam to draw a mirror image?
Yep. They can ask you to draw the mirror image. Here is what you should be doing. Take this thing, this, what molecule it was. And draw a dotted line in the middle to show the mirror, and then draw a reflection. Dotted wedge. So CH3, C2H5. This one is dextro, this one is levo. Why dextro? Because the wedge is towards the right. So right hand is the, I don't know, dextro or something. Latin se aaya hoga. And this one is, the wedge is towards the left, so that is levo. So dextro and levo. Two different isomers. By the way, the molecules that I showed you, these two molecules, they are interesting molecules because the lower one is aspirin, the medicine we use for headache. This one, that's aspirin. And the other one is, it's an antibiotic, amoxicillin. So it's very interesting what compounds you can make from basic organic chemistry. All right, let's look at this one. This molecule is equally interesting. This is vitamin C. What groups does it have? So these four, what are these? Hydroxy, alcohol groups. And this one is carbonyl, C with double bond O. And this one is ether. It is two carbons attached to one oxygen. All right, so these are different. All right, that's good to know. That's good to know because all these questions that we were doing, basically these are given to the these were from a worksheet given to the MIT class of organic chemistry. Anyways, so you guys are smart. Wow. Okay, moving on. The next thing that I'm going to talk about, maybe now we have to talk about how do organic reactions happen. And for that, we have to look at something called reaction mechanism. Now, reaction mechanism is a very important thing to understand because it plays a fundamental role in how different organic compounds are made. And secondly, because it builds up the vocabulary for effective communication of all the organic compounds. Not just that, reaction mechanism usually comes for 4 or 6 marks in your exam. All right, so the first idea is how do you break a bond? So if you have a single bond, this single bond, everything else that's attached to, I don't care. Let's suppose I have this single bond here, or maybe it's just between carbon and chlorine. What's happening? Basically, carbon is sharing an electron with this chlorine. Of course, it's sharing the other 3 with something else, but I'm not drawing that. Now, I have 2 different ways in which I can break the bond. One way is that when I break the bond, I just break it in a way that every atom here gets equal share of electrons. So this carbon goes to the right with its own electron, and that chlorine goes to the right with its own electron. Both of them get 1 electron. This bond breaking is called fission. And because both of them are getting the same equal number of electrons here, obviously in one bond there's 1 electron, 1 pair of electrons, we call it homolytic fission. Homolytic fission. All right. And what happens? Each of them gets 1 electron. So we show it as a half arrow. So this gets 1 electron, this gets 1 electron. Okay, so this is basically supposed to be a half arrow. Notice that a curly arrow always shows, this means a pair of electrons, and this means 1 electron. Okay, that 1 electron going, and that means 2 electrons going. A curly arrow is supposed to show movement of electrons. Okay, and homolytic fission is when you have both the atoms get equal shares. So for example, if I start with, all right, so let's say we have hydrogen gas and we do homolytic fission on it. So what happens is that you get 2 hydrogen atoms, each with 1 electron. We can show them as H with a circle on, or this dot on it. And we call this free radical. What's a free radical? What's a radical? Radical is a particle with an unpaired electron. Now, there are multiple ways of looking at what a radical is. For example, you can think of it as something with an orbital that is half filled because it has 1 electron. So that's definitely going to be half an orbital, right? So this is a radical. You can get radicals in many different ways. For example, if I take this compound, let's say, and I break it, and I break it through homolytic fission, that this gets 1 electron and this gets 1 electron, then what happens is that I'm going to get CH with an electron unpaired and Cl with an electron unpaired. So I've created 2 radicals, and they're free radicals. Usually we call them free radicals because they're free to move around. And this one is chlorine radical, that one is methyl radical. Okay, so radicals are very reactive. Obviously they have 1 electron that they need to pair with something else, and that they come out to be from homolytic fission. Notice that in this diagram I'm not showing any other electrons. I mean, there is 3 other electrons on carbon and 6 other electrons on chlorine, but I did not show them here because that's not relevant. All right, so do you understand? Homolytic fission is when a bond breaks and every atom or every particle involved gets equal share of electrons. Okay, so that's homolytic. There's also heterolytic fission. Again, fission is bond breaking. hydrolytic fission. When they break, both don't get equal share. So let's look at HCl, for example. HCl has this bond. Now, when you put it in water, what happens? This is something you've been doing from grade 9, that it forms hydrogen ion and chloride ion. But did we ever stop and think about it? Wait a minute. This is covalent bond producing ions. A covalent bond, a covalent compound suddenly makes ions when you put it in water. Why? In O levels, we were so obsessed with knowing, oh, there is free electrons here, oh, there is free ions here. And suddenly we have acids that have ions and nobody stopped to think about them. How come we have ions coming out of a covalent bond? And the reason this happens is that, let's look at this HCl molecule. You have a chlorine here and they're sharing one electron pair. Of course, there's other electrons on chlorine. Now, when this breaks down, water does something to it, obviously because of its hydrogen bond. Water makes the hydrogen lose its original electron. That original electron is also left to the chlorine. And what happens? Chlorine gets both the electrons. So now you get a hydrogen ion, and this has obviously a positive charge on it because it has lost an electron. And you also get this chloride with both the electrons. I'll just erase this circle. Yep. And this chloride with these two electrons that it got from one of them, it got from hydrogen, making this. We can show this through a curly arrow. This curly arrow shows that both the electrons in the bond move to chlorine. And what does that make? This is called heterolytic fission because the bond is not breaking equally. There is uneven breaking of the bond. But not just that, it will give a positive charge to one thing and a negative charge to the other thing. So there are three new terms here to understand. Have you heard of this term called sapiophile? Sapiophile is basically a term, somebody who likes humans. For example, dogs, they like humans in general. Now, phile is basically a word for liking, having an attraction to something. All right. So if I think of something with a positive charge, what it's going to attract, like this chloride over there, this has a negative charge. So, and that H positive has a positive charge, obviously. This one is going to attract positive charge. In the atom, what has the positive charge? Nucleus, right? Nucleus has a positive charge. So we call this thing, the thing with a negative charge, we call it nucleophile. Now this is a new term. Every anion that we have been calling anion in inorganic chemistry is now going to be called nucleophile. So what's a nucleophile? Just an anion. Why is it called nucleophile? Because it attracts positive charge. Okay. Every nucleophile is negative because it has this lone pair of electrons. Why? Where did it get it from? From this heterolytic fission. And every positive thing, every cation will now be called electrophile. I don't think there's an explanation required. It attracts electrons. So nucleophile has a negative charge, lone pair, which gives it the negative charge. An electrophile has basically lost an electron, and this is a positively charged thing. Now, if that new electrophile has a carbon there, for example, let's say there's a bond between this bond and I do heterolytic fission on this. So now for some reason, this breaks in this way. The electrons are given to, both the electrons are given to bromine. I will end up with methyl, but now methyl is not methyl radical. It is methyl electrophile. There's a positive charge on the carbon. And there will be bromide, which just got 2 electrons, and it's a nucleophile. Now, this thing will have what we call carbocation. All right. So that's a carbocation. Now, here's the thing. These carbocations, they come in 3 different categories. One we call, and again, it's not like carbocations come in 3 different categories. Every organic compound can be considered in that. Basically, if one carbon is attached to no other carbon, or at most one carbon, you'll write it as R. And let's say the others are hydrogen, or even if this is also hydrogen, we call it a primary carbocation or a primary carbon. So if it has a positive charge, it's a primary carbocation. Now, if this is attached to 2 others, like instead of having a hydrogen here, there's also an R here, a carbon here. We call it a secondary carbocation. And if there is a 3 carbons attached to it, we call it a tertiary carbocation. Primary, secondary, tertiary. Now I'm going to give you another term. Any organic species, or even inorganic species, everything that's attached to carbon can be divided into 2 categories. We call some of them activating groups, and these are usually the ones that provide electrons. All right, they provide electrons. And obviously, if something provides electrons, what charge does it get? Positive. So we say they have positive inductive effect. And there is the deactivating. They pull electrons. So they have a negative, but we don't use that term in A levels. We don't say negative inductive. We just say they pull electron. They're deactivating groups. For example, carbon, and in fact, all alkyls, methyl, ethyl, propyl, butyl, all of them, we show them as R. They are activating groups. But if there is a ring like this one, this is a deactivating group. So if R is attached to something, it will give it electrons to that thing. It will push electrons towards it. And if our arene is attached to something, it will pull electrons towards itself. We say that this is electron donating and this is electron withdrawing group. So one thing that you should know is that electron donating groups make positive more stable. For example, if this carbocation, if you look at this one, is attached to one alkyl, that alkyl is giving electron to this positive. So positive is going to be stable. And over here, it's getting that from 2 of them. It's getting electrons from 2 of them. And here it's getting electrons from 3 of them. So this one is very stable. So more stable, less stable, even less stable. Because it's attached to activating groups, positive inductive effect. So what is the electrophile looking for? This is an electrophile. This is a carbocation. It's looking for something with lone pair, something with a negative charge. And what is the negative charge looking for? It's looking for something with a positive charge, something with a gap, an empty orbital. All of these reactions are acid-base reactions. What? They're acid-base reactions? Yeah, because you have a lone pair and the other is accepting a lone pair. That's an acid-base reaction right there. So nucleophiles are bases and electrophiles are acids. That's a lot to digest, I know. So I'm going to stop here. And if you need more time, if you need me to go over these things, just let me know, because I don't mind spending a few more days on this, because if you understand these things, you will have a much easier time learning organic chemistry. But if you struggle with these, everything is going to basically damage the shaky foundation that we built. Okay.